Hi guys, so today we're just going to be going through A-level chemistry, acid, bases, and pH. We're going to be looking at what acid is, what base is, and we're going to be looking at how to figure out the concentration of strong acids. Let's get straight into it. So, from GCSE, you were probably told a lot about acid and bases. However, at A-level, we look at a specific type of acid and a base. This is known as a Bronsted-Lowry acid and a Bronsted-Lowry base. There's so many different definitions to what an acid is and what a base is. There's the Arrhenius acid, there's the Lewis acid, but the one that we focus on is the Bronsted-Lowry definitions. So, a Bronsted-Lowry acid is a species which donates a hydrogen ion. Anything that donates a hydrogen ion now is now an acid. And a Bronsted-Lowry base is a species which accepts a hydrogen ion. So from now on, if you see something that's accepting a hydrogen ion, that counts as a Bronsted-Lowry base. We're going to look at three examples. So the first example is quite a generic one. Everyone will be able to spot what the acid is and what the base is. Hydrochloric acid is obviously the acid, and sodium hydroxide from GCSE was the base. That's a normal neutralization reaction. Let's have a look at step 2. Step 2, we have HCl reacting with water. Now you can see we have a little reversible symbol which we're going to be talking about in a second. But HCl is actually going to be donating a hydrogen ion to water, which is quite unusual. You probably haven't seen this before. So this is the acid, and since now water is accepting a proton, that's our base. And therefore you get this whole brand new ion. This is known as oxonium ion. As we mentioned, it's reversible, so what can now happen is the reaction can go in the opposite direction, but this time this could be the acid, and this can donate its hydrogen ion back to the chloride ion, and that can be the base. And let's have a look at step 3. Step 3 is quite an example that you might see quite a lot in organic chemistry, especially in year 13. We have sulfuric acid and nitric acid reacting with each other. Now, that's quite unusual, two acids reacting with each other, but it can happen. Sulfuric acid is actually the stronger acid because it's diprotic. We're going to be looking at what that means in a second. And that is therefore the acid. And what will happen is it will donate its hydrogen ion to the nitric acid. Now, nitric acid is still an acid. However, since it's now accepting a proton, it's now classed as a base, which is quite unusual. And therefore, you produce H2NO3 plus and HSO4 minus. This has lost the hydrogen ion, and this has gained a hydrogen ion. And as we mentioned before, since it's reversible, the reverse direction can happen, where this can act as the acid because it has an extra proton and can donate it back to this, the base. So those are just a couple of examples of acid-base reactions just happening, and where they can happen in unusual circumstances. Now let's look at what a strong acid means and what a weak acid one means. So a strong acid is something that completely dissociates to release hydrogen ions, but a weak acid partially dissociates to release hydrogen ions. Your strong acids are things like HCl, sulfuric acid, nitric acid, whereas your weak acids are carboxylic acids. Any carboxylic acid is a weak acid, literally anyone. Things like benzenoic acids, which they'll throw in the exams to put you off, that is a weak acid as well. Strong bases completely dissociate to release hydroxide ions, and weak bases partially dissociate to release hydroxide ions. Now, a strong base is things like sodium hydroxide, barium hydroxide, strontium hydroxide, especially these two. Since they have two hydroxide ions, they'll release double the amount of hydroxide ions upon dissociation. And weak bases, as we mentioned, water can act as a base. It can accept a hydrogen ion and become an oxonium ion. That's a weak base. NH3, that's also a weak base. Now, you might notice magnesium hydroxide is a weak base as well. That's because it's based on solubilities, and this doesn't dissociate completely due to solubility. At AQA, they call it sparingly soluble. and you have to use that key phrase. Okay, as we mentioned just before, we had the word diprotic acid come up. Now, anything that's a monoprotic acid releases only one hydroion. Diprotic acids can release 2 hydroions, and triprotic acids can release up to 3 hydroions. So anything with 1 hydroion is a monoprotic, anything with 2, like H2SO4, is a diprotic, and anything with 3 is a triprotic acid. And this is super important when working out your pH of strong acids, because you'll have to look at your ratios and look at your equation of dissociation, which we're going to be having a couple examples right now. So pH, first of all, what is pH? pH is a measurement of concentration of hydroions. The pH uses something known as a logarithmic scale. So that means the logarithmic scales are used quite a lot in biology and chemistry. You see them sometimes come up in maths as well, and they simplify huge range of hydroions concentrations. It can be very small, very large, but if you use the log function, which will look something like this on your calculator, or it could look like this with a little square, or it could look like this. They're all the same. They're all usable. If you have the one where you have to input a number in, you put it as 10. If you have one that doesn't have a number, that's still automatically putting it as log 10 for you. And if you have one like this, that's perfectly fine. Now if you import a really, really massive number, so I'm going to do 10,000. I've now got, when I do log 10 of 10,000, I instantly get 4. It simplifies and condenses numbers for you. That's what the log scale is used for. And it's really, really useful when it comes to pHs. Also, a little fun fact is that the little p, when we're going to be using it, you're going to be seeing it quite often. It literally just means minus log 10. So whenever you've been using the phrase pH, all you've been saying is minus log 10 of H. That's where this equation comes from. pH equals minus log 10 of hydroions, and your hydroion concentration. That's really important. The square brackets emphasize its concentration you're looking at. Your pH should also always be rounded to 2 decimal places. It's just how chemists do it. And if you're given the pH already and you need to find the hydroion concentration, you need to do the inverse function. The inverse of minus log 10 is 10 to the minus of whatever it is. So in our case, it's 10 to the minus pH, and that will equal your concentration of your hydroions. We're going to be using those functions now. So how do we find the pH of strong acids? So let's have a look at this first question. Find the pH of 0.0100 or 0.01 of HCl. So first of all, you're not always going to know, and they're not always going to explicitly tell you that this is a strong acid that you're dealing with. You have to be able to identify that. HCl is a strong acid. So when I do my equation of dissociation, I know all strong acids completely dissociate. All my HCl molecules will be converted to H plus ions and Cl minus ions. And if I have 0.0100 of this will also be 0.001, sorry, 0.01, and this will also be 0.01. It will completely dissociate to release and give me the same amount. Now, I can now put pH equals minus log 10 of my hydroions concentration. Do I know my hydroion concentration? I do. My hydroion concentration is 0.01. So I do pH equals minus log 10 of my 0.01. Make sure to get rid of the square brackets. You're now, because you put a number in, you can now use round brackets. So minus log 10 of 0.01, and that's giving me a pH of 2. Now it's giving me a pH of 2, but I have to put 2.00 and make sure it's in 2 decimal places. Let's have a look at the next one. Find the pH of 0.01 of H2SO4. This time, let's identify, is that a strong acid? It is. So H2SO4 will completely dissociate, and this time it will release 2 hydrogen ions and an SO4 2 minus ion. And now I can write the equation pH equals minus log 10 of concentration of hydrogen ions. Now I have my 0.01 here, but for every 1 molecule I have of this, I have 2 lots of hydrogen ions that I'm producing. That means if I have 0.01 of this, I'm going to get 0.02 of this, double the amount. And this, because it's in still a 1-to-1 ratio, the sulfate ions are going to be 0.01. That's because it has a ratio of 1. But I don't need to worry about that too much because my pH is equal to minus log 10 of my hydrogen ions. So all I need to do now is put the 0.02 into my equation. Putting that into my calculator, it will give me 1.6989. 1.6989 ... And to round that off to 2 decimal places, that's 1.70. Perfect. Now the pH of a solution of HNO3 is 1.75. This time we need to find the concentration of hydrogen ions. So remembering that inverse function is 10 to the minus pH, and that's my concentration of hydrogen ions. If my pH is 1.75, I just put that 1.75 in the top left corner, top right even, and that will give me my concentration of hydrogen ions. So putting that into my calculator, I get 0.01778 ... and that number keeps going on in my calculator. And now just to round it off, I'm going to round it off to 3 significant figures, 1, 7, and 8. Perfect. And that's how you figure out your concentration of hydrogen ions and to find your pH of strong acids.